Hello guys, welcome back to 5-Star Physics. Today we're just going to be talking about vertical components, vertical velocity, and how you can use it to solve also for horizontal. So let's start with a practice problem here. So a ball is thrown off a 1 meter cliff at a velocity of 2 meters per second to the horizontal. Find distance traveled horizontally, or delta x. Okay, so first thing we're going to do, draw a picture. So 1 meter high cliff. We know that the ball is thrown off, so it's going to look like that. It has initially 2 meters per second to the right, and we are expected to find delta x. Okay, pretty simple. And so let's also do our second step. So we have delta x here. Our components, time. And then we're also going to do vertical components, because now we're also tying in our vertical components in order to help us solve, and you will see. So let's list it all out. We know we're solving for delta x. We know our initial velocity is 2 meters per second to the right. But we also know that our final is also 2 meters per second to the right. And this is important to know. This is a pattern. This is not just this problem. It's in every single projectile motion problem. These two are actually the same in this case because once the ball gets to this point here, to its max, it's going to be constant at 2 meters per second. Once it reaches that last point here before it starts to go down vertically, it's still going to be at 2 meters per second, right? But then now it starts to have a Vy component that's going to pull it down, down, down to the ground. So in this case, Vx is also 2 meters per second squared. Now we don't know acceleration. We know delta y is negative 1 meters because for height, in this case, the final is 0. The height is 1, so it's 0 minus 1, right? We know that this is 0 meters per second because there's only a horizontal component here. Okay, there's no vertical component. That's also a pattern that occurs. We don't know the final Vy, and we know that Ay is, of course, negative 9.8 meters per second squared. Notice that time is the same for both delta x and delta y. That's important because that's going to be our connecting factors, you will see. So if we're solving for delta x here, then how would we be able to do that if we only have two variables? We only have the initial horizontal velocity and the final horizontal velocity. So there's no way to solve it just using horizontal equations, which is why we have to tie in our vertical equations. So let's do that. So as you can see, as we just figured out, time is a connecting factor. So let's solve for time so that then we can use time in this equation. And if we get time here, we'd have 3 variables filled out, and then we could solve for delta x. So let's do it. Delta y, we need to do the one without the final vertical velocity. So that's going to be this one. Minus 1/2. Make sure that you always write your subscripts. That's important so you don't get mixed up. And then we know that this is 0 because the initial vertical velocity is 0. And then we just solve for time. Algebra, and that's actually going to get you to, if you plug in all your variables, it's negative 2 divided by negative 9.8. It's going to get you to 0.45 seconds. You should be able to do that if you plug it into your calculator. Okay, so now we have to go back and fill this out now. So we know this is 0.45 seconds, okay? So now that we know that, all we need to do is use an equation without acceleration to be able to solve for delta x. So let's do that. We know that that equation is delta x equals 1/2 Vi plus Vf t, okay? And so then we just plug in our values. 1/2 4 times 0.45. And you should get delta x is equal to 0.45. Oh, sorry. Oops. No, that's not right. You should get that's equal to 0.9 because it's 0.45 times 2. So should get 0.9 meters. That is your final answer there. So you see how I did that. You see how I connected time with the vertical and the horizontal components to be able to solve. Now, what I did not mention is that a of x in this case did actually equal 0 meters per second squared. Although, that's not always a guaranteed, but in this case, it was okay to assume because there was no horizontal acceleration. As we know that it was constant at 2 meters per second throughout the entire process. So we could have put that there as well, but I wanted to show you how to solve using vertical to horizontal components. Okay, so let's talk very, very quickly about something called relative motion. Relative motion is basically how motion is observed through different reference frames, and how it can be used to predict motion in another reference frame. Pretty much all that means is, from your perspective, how do you see it moving? For example, say you are this person in an airplane, okay? Doesn't really look like it, it's fun. You're looking through a window. What do you see? Well, you don't see the plane moving at 500 meters per second because you're in the plane, but you see the ground moving to the left, okay, at 500 meters per second, to the left, right? But say you are then this guy on the ground looking up at the plane. Well, you're just going to see, since you're on the ground, you're not going to see the ground moving to the left 500 meters per second. You're going to see the plane moving to the right with 500 meters per second. So all that goes to show is just, it's about how you view it. It's about your reference frame. It's all about where you are in regards to the object that you were talking about. And that's just going to change the way it looks to you. Now, I just want to really note that this is not really going to be on the AP exam. When I took my AP exam last year, I don't think there was maybe even one relative motion question. Definitely not on the FRQs, maybe one on the multiple choice questions, but for the most part, it really is irrelevant. The last concept I wanted to talk about in this video is called linearization. Pretty much it just means making your graph, your line on the graph, straight so that you can be able to calculate area and slope. Because as you know, you can't find the area of a curve. Look at this graph here. How would you find the slope? How would you find the area? You can't, because it's impossible to know without having a straight line. So pretty much then that begs the question, how do I plot it so the slope is AY? So how do I plot it so I can get this variable? And this is how you do that. So first, you would still do it like you're solving any other problem. So let's list out our variables. So we know that we have delta y. Yep, we have it. It's given to us. We know that vi, let's say that since we're solving for ay, in this case, it's 0 because we'll say the object is dropped. Okay, this is just a hypothetical situation, right? We don't know vf, okay? We're solving for acceleration due to gravity, and then we have time. Okay, our data is giving us time. So we know that we can solve like any other equation, but we don't actually have real values here, okay? And if those values are changing, you can't just, solve necessarily. So you need to use a graph. The way to do that would be to still use tools to solve, step 3, but just in a different way without actually having to plug in numbers. Let's do that. Let's find the equation without VF, okay? Delta y equals VIT plus 1/2 AYT squared, okay? Know that this is 0. So delta y equals 1/2 AYT squared. Okay, pretty simple, right? But now, all that we need to do is that we know that we're solving for AY. And if we know also that slope equals y over x, then AY simply has to equal some variable, some group of variables y over some group of variables x, and that is how we would make that line. So let's do that with this here. So let's isolate AY. AY equals 2 delta y over t squared. So then that means that this is our y and this is our x, okay? So then if we were to plot this on a graph, 2 delta y and then t squared, do you know what we would get? We would get a straight line where the slope would be a y. Now, It's never going to be this simple. It's going to get more confusing. You're going to have to do this with a lot of different other concepts along the way, but this is the base concept. You're isolating a variable to pretty much get a fraction where that the top value is your y, the bottom value is your x, and then when you plot those on a graph, you're going to get a straight line, and the slope of that straight line is going to be your acceleration. Okay, so I just have a couple quick takeaways for you. The first one is that time is going to be your connecting factor between your delta x and your delta y. Okay, so to be able to go from delta y to delta x or delta x to delta y to solve for one of the variables, you have to use time. Time is going to be your connecting factor between those two. The second thing is that for linearization, like I said before, make sure that you're isolating the variable you're solving for. Okay? And it always has to be left alone. There can't be anything multiplied by it, divided by it, added to it. It always has to be by itself. But also know that you can still use that problem-solving process just like you do when you're regularly solving an equation for linearization. The only thing that you don't have to do is plug in your numbers, which may actually make it easier. All you have to do is just solve for the variables and then just know that your y's in your numerator, your x's in your denominator, and just plot those onto your graph. And then whatever you're solving for, whether it's the slope or the area, that's how you're going to find your unknown variable. Thank you guys for tuning in. That is the end of kinematics. So my next video will be talking about dynamics and forces and the new unit.